In the last video, I talked about transactions and Bitcoin tokens when we started to define this interface between Bitcoin applications and Metanet clients or wallets or service providers. In this video, instead of talking about transactions and tokens, which define the core of this interface, so you should watch that one if you haven't already, I will be talking about data encryption and how we can create systems that allow users to exchange data with one another and protect its confidentiality during those exchanges, even if the data is sent on the blockchain within Bitcoin transaction outputs or via other insecure communications channels. So how do we think about encryption within the context of Bitcoin? Of course, we don't have to, and that's the point. Bitcoin is not an encrypted system. It does not use AES. It does not use other encryption algorithms, and there is no hidden or masked information at the Bitcoin layer. The blockchain provides a vehicle by which functions can be defined within the context of Bitcoin script, and by which data can be stored and retrieved via stack elements pushed onto the Bitcoin virtual machine, which defines the execution environment for programs running within Bitcoin. But all of that is fairly low level and perhaps beyond the scope of what I'm talking about. It's not beyond the scope, it's getting a little bit into the weeds, I guess, here at the beginning. So Bitcoin doesn't require encryption. Bitcoin is an open and transparent system, and it does not use encryption routines. It uses digital signatures to secure coins, but encryption is a different process. So why are we talking about data encryption within the context of Bitcoin applications? Well, it might not be necessary for Bitcoin, but users find it useful, and application developers find it useful. We have within Bitcoin these keys that store, they don't store, but they provide the ability to unlock Bitcoins that are stored in various outputs on the blockchain. And we also have users who need to have custody over those keys so that they can interact with Bitcoin tokens. So Bitcoin doesn't require encryption, and applications will certainly emerge that don't use these functions. However, when we have users that hold keys, and when we have the ability to pay for things with Bitcoin, it means that we can create applications that might want to use encryption and that might have the correct economic incentives to provide it. When users engage with the Bitcoin network, they use micropayments, or they have the capacity to use micropayments. So small amounts of Bitcoin that pay for services directly. In the ad-based model for the internet, there is no capacity for micropayments that directly facilitate value transfer between users. However, in a system that facilitates this functionality, such as a Bitcoin-powered application, so to speak, it becomes more workable to encrypt data and protect user privacy. When users pay for the services they are consuming through the applications they use, then the applications have an incentive to serve the interests of the user more so than, for example, an advertising platform or a data silo. Therefore, the incentives are aligned within a large number of Bitcoin applications to provide functionality that allows users to make use of the keys that they have, which they need for Bitcoin, to also protect the privacy and the confidentiality of user-held information. And thus, for applications that want it, we can provide the functionality within a wallet to application interface, enabling applications to encrypt and decrypt data with user consent and with user keys. All the while, the application does not need to manage and in fact cannot access or learn the key material itself that is used in the encryption process. How can this be achieved? So suppose we want a function for encrypting data and we want a function for decrypting data. In the simple case, you provide the data and then you get an encrypted copy of it, or you provide the encrypted copy and then you get the data back. That would be the naive implementation. So two new functions get added to our wallet to application interface for encryption and decryption. Very simple functions at that. However, this does pose a problem. This implies the use of only one key. And certain classes of data ought be kept separate. It also only allows data to be encrypted for the single user and not between users. It would be nice to extend this and make it more open-ended. The more open-ended we make this interface, this specification of a boundary between Bitcoin applications and Metanet clients or wallets or service providers, we can provide for more applications to meet more of their requirements through this interface when it is more open-ended, right? So we should try to make this encryption function a little bit more powerful. In our naive example, we have a user who has a key. Well, the user doesn't have the Metanet client or the service provider or the wallet that the user is using manages a key, and that key is used to encrypt some data, right? And then it can be used again to decrypt that data. But if suppose even in the case that it's just this one user and we're not talking about exchanging data between users yet, suppose I have my diary and I have an application that is a diary and it encrypts my diary entries using my user key and using the this interface that we're defining here with a Metanet client or a wallet. And then when the user goes to read their diary later, the encrypted copy of the diary entries are fed back through the decrypt function, and then the plain text versions of those are accessible once again, right? Now, suppose we put these encrypted texts on the blockchain, right? Now, when a Bitcoin transaction output is created, the transaction output contains encrypted copies of diary entries, and those become public. Even though they're encrypted, they're public. It would then be possible for any other application to emerge which learns through the public nature of this data the encrypted copies of the diary entries, and then goes back to the user and just says, hey, can I use the decrypt function really quick? And then decrypts them. And suddenly this auto insurance application or something has access to my diary entries. So this is not ideal. There are different classes of data. And even within a specific class of data, there is a need to have different keys used for different operations. So classes of data, and then keys within each class. Key universes for a class, and then specific keys within that can be defined. This makes the architecture a little bit more powerful. Why? Well, because if, for example, in my diary application, I have a specific class of data called the diary, right? And we're going to call these protocols because it's really an understanding about the specific type of data and the specific context in which this data is being used. And that's really what a protocol is. It's an understanding about these things. So the diary protocol, right, which deals with the diary class of data. And so this specific type of application, called a diary application, can now encrypt diary entries with the diary protocol. So the parameters to the encrypt and decrypt functions now expand. Not only do we provide just the data that we want to encrypt, but we also say the protocol that we want to use for encryption. And this protocol is a unique identifier that denotes the specific context in which this data is being encrypted or decrypted. The service provider or MetaNet client or wallet or whatever will then use the protocol ID, the protocol identifier, as well as the unique and specific key within that key universe to arrive at a specific key used for encryption. How this is done is beyond the scope of the specification, but there are various ways of deriving new keys for users and then using them in this process. So now we have an open-ended way for applications to encrypt data with a user-held key under a specific protocol. And further, multiple keys can be used in the key universe of that specific protocol without the need to make a whole new protocol. So we have the diary protocol, and then maybe key ID 1 within that protocol ID would be for the first diary entry, and key ID 2 would be for the second one, and so forth. And the rules that govern the use of the key ID are defined by the specific protocol we are now using for data encryption within the applications that implement this protocol. How does this relate to the solution for, well, somebody could learn my decrypted, or somebody could learn my encrypted ciphertexts and then sort of use the decrypt function to simply access my data? Well, now there's a protocol. Now a user can be prompted transparently to the running application whether they're okay with that application using this particular protocol in this context. So if I'm using my auto insurance application and I see a pop-up that says that it would like to access data encrypted using the diary protocol, well, I would obviously see something is wrong there. Why would it need to access my diary entries in order to give me an auto insurance quote? Clearly, I mean, these insurance companies, I get it, they want to be nosy, but that's going a little too far, I might think. So, now the user decides whether an application gets to use a specific protocol, and then once an application is granted a specific protocol to use, then all of the key IDs under that protocol can be freely used by the application to perform encryption and decryption operations. So that's really the beginning of the solution. I mean, now applications can encrypt certain classes of data, certain types of data, under specific protocols with different keys, because keep in mind, each protocol is its own key universe, and then each key ID inside of that protocol is a unique key. This implies that when the encrypt function is used with, for example, diary protocol and key ID 1, then the decrypt function must also be called with the same parameters, the same protocol ID and key ID as the encrypt function, in order that the data be successfully decrypted by the application making the request. The application also needs to provide the ciphertext that it wishes to decrypt in this context. how that ciphertext is tracked and managed by the application is beyond the scope of this wallet to application interface. So now we have local per user data encryption using key IDs and protocol IDs so that there's no reuse of keys for multiple things, or at least that intelligently designed protocol IDs will stipulate that key IDs are to be perhaps generated in some deterministic way, or otherwise not always just the same one every time. And users are in control of how data is encrypted, by which applications it is encrypted, and can make informed decisions about how their data is used within particular applications, even going so far as to potentially revoke an application's access to a particular protocol at a later date if the user switches to another application in the future which knows how to deal with that same class of user-held data. So that's how we can protect the privacy of user data when only one user, the primary user in this example, right, that we've been talking about, wants to be able to access and manage their particular data. When a couple of users want to talk to each other, it gets interesting. Now, when two users want to exchange information, of course they're going to need to exchange information over some communications channel which exists between them. That communications channel is beyond the scope of the wallet to application interface because that is managed by a particular application. Applications might facilitate user communication in a number of ways, including by using the blockchain or by using other means. Either way, we will assume that users have a means of exchanging information with each other over a communications channel for the purposes of defining a specification by which user data can be encrypted between users. So, this is going to introduce, beyond just having a simple encryption and decryption key, principles of public key cryptography, where now there are public keys and private keys for the users. Each user has a root identity public key and a root identity private key. Of course, these keys can be rotated if desired by the service provider or the metanet client, etc. But that key rotation is beyond the scope of this wallet to application interface. Because when keys are rotated, then the protocols would need to define at some higher level a way to roll over the data to the new key, and those definitions would overcomplicate the base protocol. But protocols are free to do that at a higher level, how data could be rolled over between an old key and a new key for a user identity. So if maybe a user loses or has compromised their identity key, that can be rotated to a new value. But for the purposes of defining the specification, we assume that each user has a public identity key and a private identity key. Now, when you have the public key of someone else and your own private key, and when they have your public key and their own private key, then those two users can derive a mutual value known as a shared secret, which means that the two users can have some value that only they two know. And that shared secret can be used in a number of different ways. In order to not get too far into the weeds of elliptic curve cryptography and key derivation schemes in this video, suffice it to say that this shared secret can be used by a sender of information to derive, using a protocol ID and a key ID, a child key for the recipient based on that recipient's public key. What all of this means at the end of the day, without going into all of the technical details here, is that we can add another parameter to our encryption and decryption functions. So we have, to review the list of parameters right now in our encrypt function, we have the data to encrypt, the protocol ID, and the key ID at a high level, right? But now we can add the counterparty, which is who is this data being encrypted for? And the default counterparty, if you don't provide one, is just going to be self, meaning that you're encrypting the data for yourself and that you can decrypt it, right? But we could also use the identity public key of another user as our counterparty. This is known as counterparty encryption. Now, when I encrypt something, if I provide the counterparty public key for a recipient user, then that recipient user, when they provide my public key as their counterparty in the decrypt function, along with the same protocol ID and key ID and the ciphertext that I generated, they would be able to successfully decrypt the data and access it in a confidential way. So the ciphertext is encrypted and exchanged over a communications channel that someone might be monitoring, but only the recipient, and only when they use my counterparty in the decryption process, my public key as the sender, as the recipient's counterparty, then, and only when the protocol ID and key ID are used in the same way for both the sender and the recipient, will the data decrypt. So there are various methodologies by which this key derivation process can be implemented. However, one specific implementation should be chosen and used consistently within this wallet to application interface to ensure that when data is exchanged between users, it is readily accessible and decryptable to all users of the system. So users can specify counterparty self when they encrypt something, and they can provide counterparty of another user's identity public key. And then, during the decryption process, if I receive something from somebody, I know the identity key of the person who sent me this thing. I know the protocol ID and key ID of the context in which I am receiving this information. And I know the encrypted information, of course, that I have received, and I can plug all of these things into the decrypt function, and then we have a way to exchange information between users across different protocol and key universes in a confidential way. And that, I say, is the most open-ended way to define a system for encrypting and decrypting user data within Bitcoin-powered applications. So that's data encryption. That's how we can do this. Extensions to this would allow for multiple different recipients, group encryption. There are ways of doing this as well, and I think it would be overly technical, and this video would go on for a long time if I were to get into the details of how this can be done, but I will say that I do have implementations that have been written and that I'm sure others do as well, and it would be the subject of a future video to discuss group-based data encryption. But for the simple case of user-specific group encryption, where you're just encrypting something for yourself, or the case where you're exchanging data with a single person, a single counterparty, it is possible to do so using existing tools and methodologies that have been fairly well accepted by large players within the Bitcoin SV space. So wallets, service providers, Metanet clients on one side, and then Bitcoin-powered applications on the other side of that interface. Now we have a way for users to communicate with one another privately, to decide how data is to be used by granting or denying specific applications access to specific protocols and classes of their data. And we have a way to allow multitude of keys to be used within a particular protocol using key IDs to prevent key reuse and to be really creative about how certain things can be encrypted within certain contexts. So I think that's all I have for this one about data encryption. So data encryption is, I would say, the second pillar of this wallet to application interface that I'm specking out here in these videos for how can wallets and applications in Bitcoin communicate, and what are some of the messages that are exchanged between a wallet and a Bitcoin-powered application over an abstract communications substrate that exists between the application and the wallet, and then how are the data structures implemented in the most open-ended way possible to facilitate the most powerful applications being built on top of this architecture. So yes, I think that's all I have to say in this one. In the next one, I will apply these same concepts to digital signatures so that we have a way of attesting to the authenticity of user data. And then because that's actually fairly similar using protocol IDs and key IDs to data encryption, I might also get into some other things about identity certificates. So stay tuned for the third video in this series, where we'll delve deeper into the evolution of this kind of interface that we're defining for Bitcoin applications. Thank you.